Well, thank you. Thank you. Well, welcome everyone. If you haven't met me yet, I'm Fernando Redivo. I'm the executive assistant for the System Dynamics Society. And we're here again for another webinar in the seminar series. And today's topic is applied system dynamics for students and beginners. And we're going to be taking you through an integrated modeling process and also give you tips on model validation and calibration. And we're very excited to present to you guys today. Thanks for joining us. And if you're not a member of the System Dynamics Society yet, would like to remember the benefits of joining the society, and starting with the benefit of free access to all society seminar series, such as this one. You also get a great discount on our conference upcoming in July. You get exclusive prices on our bookshop, full access to the Society Scientific Journal, the System Dynamics Review. And if you're planning to learn more System Dynamics, you get a discount on our partners' online courses. And of course, the best way to network and get to know people in the field, it's being a member of the System Dynamics Society. And if you haven't registered yet for the conference coming up in July from 25 to 3rd of July, you can do it so on systemdynamics.org/conference. And if you enjoyed the seminar series, we have 2 upcoming webinars. The first one happening on April 7 with women in system dynamics. They're going to share their experience and their background. And this is going to be an open conversation, and I hope you guys join there. And we also have another one later on April, 21 of April, which is the effect of institutional quality on economic growth. And you can register for both webinars on systemdynamics.org/events and get more information about them there. And I'd like to thank all the sponsors of the society. It's only through their help and support that we're able to expand the field of system dynamics society, the field of system dynamics. And if you'd like to sponsor the society, please reach out to me and Rebecca at office@systemdynamics.org. We can start a conversation from there. And just a small disclaimer, guys, the works that we present here in the seminar series have not been subjected to review, which means that they can contain some small errors or omissions. But we do share this work in the spirit of openness and collaborations and learning. And if you'd like to send us feedback, please do so using the survey that we usually send out right after the seminar. And just a small agenda for today, we're going to have 45 minutes presentation and then 30 minutes of Q&A and discussion. And if you'd like to engage with the presenters after the seminar, you can just stick around and talk to them for about 10 minutes. And by now, if you attended the previous seminars, we're going to be using again the poll everywhere for the Q&A session. And I'm going to go ahead and just give you 1 minute to reach to this website. You can also scan the QR code on the screen or go to pollev.com/STS-post877. And there's also going to be a link on the chat. You can easily access the platform, and we can start getting used to the platform with just a small 2 questions. First, just getting to know where you guys are from. Just going to give you 30 seconds to do that. Again, you can join with the QR code or the link in the chat. Some people already answering the question, which is people from Italy, Belgium, Colombia, USA. I'm very excited to have people from Mexico, Germany, and Brazil. So yeah, we're covering a lot of time zones today. It's always very exciting to share work with such a broad and diverse community. Thank you so much. And I have just one more small question for you guys. Just 1 second till it loads. So I'm really interested in getting to know our community, our broad community or worldwide. And I've been bringing here questions to get to know you guys a little bit better. So today I really want to know which superpower would like to have if you had a superpower. Start with mind reading, maybe invisibility, teleportation, flying, or maybe you already have one. I'd love to know which one you have, but please go ahead and share with us. Let me just click here to share the show responses. So people really want to teleport. I mean, nowadays in COVID times would be a great one, right? Flying, that also works now. Mind reading, invisibility can be very helpful. And the 14% of people that already have a superpower, maybe put in the chat what you have. Well, thanks so much, guys. I think you guys got used to it. I'm going to leave the Q&A open, and you can ask your questions and upvote the ones that you most like. And at the end of the presentations, the presenter is going to answer those questions. And today we're here with Andreas Botta from the Witwatersrand University and Nalini Pillay for Eskom Holdings. They're both part of the South Africa chapter of the System Dynamics Society. And we're very excited to have them here. So I'm just gonna head over to Nalini. I'm gonna start. Thank you so much, guys. Thank you, Nalini, if you be kind enough to start.
Okay, I will just try and share my screen. And here we go. Okay, this should be visible. Can I get confirmation?
Yes, I can see. I think everyone can see it. Thanks, Nalini.
Perfect. So since we have so many people from around the world, it's a very good morning, good afternoon, good evening, good night. It's great to have everybody actually attend our seminar. Like Fernando said, I'm Nalini Pillay. I will present the first half of the seminar, and my colleague Andries Botta will then present the second half. A lot of the material that we cover here is actually from our newly published book, which is Applied System Dynamics with South African Case Studies. So I hope you find it interesting, and if you go away with at least one new bit of knowledge, I think we've achieved our objective. So before we get into the presentation, I just want to try and tell you guys a little bit more about South Africa. So where are we? South Africa is found on the southernmost tip of the continent of Africa. And we have over 59 million people. Our president is Cyril Ramaphosa. And we're known as the Rainbow Nation. When Andries puts his camera on, you'll realize why. But no, actually, it's because of our diverse and our diverse cultures, and the fact that we have so many different people of different cultures. We also have 11 official languages. In terms of some interesting facts related to South Africa, I think the biggest plus is that we have the largest beer brewery in the world. Now, how's that for a high five? Come on, guys. Like, I should hear some applause for this. But besides having the biggest beer brewery, I mean, we take up about 1% of the land mass, but we actually have about 10% of species linked to birds, plants, and quite a lot of animal species as a fraction or as a proportion of the world's species. We also have more than 90% domination in terms of our platinum resources and over 41% in terms of our gold resources. So here on the slide, you can see some of our beautiful cities. We have the city of Johannesburg, which is in the Gauteng province. We have the city of Cape Town, which is in the Cape province. We have the city of Durban, which is in KwaZulu-Natal. And those are just 3 of our 9 provinces. So that's enough about South Africa. I hope I sold a little bit of the country to you. So we'll just go through an introduction and then through some definitions before we get into the modeling approach. And then it's followed by some interactive or live demonstrations to show the difference between validation and calibration, and then we'll conclude. Now, before we get any further, I'd like to ask you this. In terms of the way in which you see yourself, would you say that you're more a pilot or an aircraft designer, or perhaps both? Maybe you can type in your responses. Now, with pilots, I mean, what's the objective of a pilot? A pilot wants to keep the plane in the air, right? When we look at aircraft designers, the objective is really design a plane that's robust, that will be stable even under extreme conditions. And when we liken ourselves to a pilot, what do we actually mean? So what we're saying is that, are you the type of person in your environment that's actually trying to carry out business as usual, your day-to-day activities, fighting fires, and overall being reactive in terms of how you approach the problems, events in your environment, etc. If we liken ourselves to an aircraft designer, in our environment, we're talking about those people that design the policies, or those people that actually plan our strategies and develop these strategies so that we can make the right executive decisions. If we look at the aviation world, or the realm of aviation, what helps us in terms of learning more about the system is if we have flight simulators. Now, in the system dynamics environment, we don't call them flight simulators, we call them management flight simulators, which is essentially our system dynamics models. Ideally, we do want to be a combination of both. Now, this might seem a little bit simple, but I think it's important for us to understand these definitions. They're very basic, but what I found is a lot of people actually use things like systems thinking and system dynamics very interchangeably. And you would think they would know better. And sometimes it's like blasphemy. I mean, they use it in like completely the wrong context. So in terms of a system, quite simply, a system is an arrangement of parts or elements that come together to provide a particular function or purpose. When we look at system dynamics, and this definition is from our book, system dynamics refers to a computer simulation method which allows for the decoding of complex system problems by incorporating your feedback loops and time delays linked to underlying system structures, so that the behavior of the system problem over time can be identified through plausible scenarios which result in emergent, counterintuitive outcomes. If you love long sentences, this one is for you. However, more than that, it's actually a very comprehensive way of including all of the main components and elements of system dynamics. In terms of systems thinking, and systems thinking, we all know, is the underlying philosophy that we need to adopt in order to try and develop these system dynamic simulations. If we look at the iceberg model, it's perfect in terms of explaining how systems thinking works. So when we come across a particular event, immediately we end up mentally modeling what we perceive is the situation. So based on our perception, based on our intuition, we have this mental image. And when we try and solve problems while on the event level, we end up being very reactive again, and we end up treating symptoms. So we end up with these end-of-pipe solutions. However, after several events, and these events could be things like newspaper headlines, for example. Now, once we go through or come across a whole series of events, we start deducing things in terms of the pattern that's emerging. And trying to then identify these patterns of behavior already takes us one step closer to actually understanding the root cause of the system. And only when we start analyzing these patterns and trying to understand them, do we end up getting one step closer to the underlying structure of the iceberg. And only when we understand the underlying structure can we design solutions, because then only would we be able to address the root cause of a problem and identify leverage points in the system to effect change. In terms of the conventional modeling method, this is just a summary of a whole number of modeling methods from various sources. So there's always the first step that involves identifying the problem, articulating the problem, and conceptualizing the system. In this step, lots of practitioners would say, it's important, listen, you have to identify the key variables, you have to understand your reference modes, patterns of behavior should be identified, and some people actually develop the causal loop diagrams in step 1. In step 2, this is largely around model formulation. So when it comes to model formulation, you would then try and establish your rate equations, define your variable parameters, do your initialization. Sometimes your model boundary chart is developed together with subsystem diagrams. And some people actually then include the causal loop diagram in step 2. In the third step, which is model testing and further development, here's where we do scenario analysis, we refine the model, we validate, etc. And the last step generally, and this is like a very generic high-level breakdown of the modeling process. There's sensitivity analysis and scenario analysis where we test different policies. Now today what I'll do is take you through the 8-step modeling process, which is the one that we explain in a lot of detail in our book. The first step is your project inception. Second is concept to context. The third is setting the boundaries. The fourth is system analysis, followed by model development and design, and then validation and policy insights, model handover, and lastly, your model maintenance and updates. So when it comes to project inception, there's 2 ways in which we get a project going. So especially in our environment, and I'm sure once a lot of people have sort of migrated out of the academic world into a corporate environment, this becomes very important. How do projects actually start? So they can be initiated either by a customer who approaches you or by a system dynamicist. In both cases, you need what we call a project sponsor. Now, a project sponsor should ideally be on an executive level. The reason for this is that you want this seamless integration between the operational model development as well as the executive management that makes all the high-level decisions. Once you have this executive sponsor, the chances of you marketing your model and getting buy-in is that much more higher. So once a project is initiated by either the system dynamicist or the customer, there are other parties that are also critical, one of which is a technical owner. Now, it might seem strange that you need a technical owner if you already have a customer. The problem is that sometimes you have a customer and this customer is so excited about the project and absolutely loves the model and uses it all of a few weeks and then shelves the model because they're busy. It's not that necessarily they don't find value in the model, but most of the times, those are the guys that are really, really pressed for time. So they'd love to use the model, but they just don't have the the capacity in terms of the available time to be able to run the model. So the technical owner then comes in, and this technical owner is the guy that engages with the model, runs the scenarios, establish or finalizes a report that management then use. And because it's actually he's familiar with the model, he can also then make the updates and changes, and it's so much easier then for the customer to actually then continue using the model. And I promise you, that's one of the things that really help to extend the shelf life of your model. The other important thing to note in the stage is, this looks like a very simple visual, but you need to know what you're solving for, right? So in terms of the variables here, you must understand what your X and Y variables will be on the axes. Now, this doesn't mean that if you're asking what the graphical output should look like, that you're already prescribing a preconceived result. Not at all. What you're actually doing is ensuring that the system variables that need to be reported on will be reported on, because you can't actually tell what the behavior of the system is going to be upfront. I mean, that's not the intention of actually asking this question. It's really to pin it down. You have a lot of customers that say, listen, can we model strategy? And then you look at them and you're like, okay, tell me how long is a piece of string? You can't actually do that. So that's why I've got you at the bottom as well. You need to understand the difference when you're modeling a system and when you're modeling a system problem. The other important things that you need to also be aware of in this step is that the model is not a crystal ball, which means that it should never be used for predictions. Now, the model has a multitude of mathematical computations, but it cannot think for the user. It does not have engineering judgment. And you need to understand what the results mean by engaging these strategic dialogues and being able then to understand what the results are. So it's not just about, can you, and we've had this as well, can you build a model so that when we click on the button, we get the answer? And system dynamics models should not work like that. The understanding behind it is just critical. The other thing is that the structure is developed in a mathematically sound way, but it will not and should not provide a bias for a predetermined result or output. I mean, sometimes you'll have somebody come to you and say, can you build a model for me? And this is what I want to show and prove at the end of the day. And then you're like, nope, we can't do that for you. That's telling us what the answer is before we build the model. And so how do these intuitive insights come about? Which is really why you want to actually develop these models and include all these feedback loops and time delays and all the nice stuff. The next step is concept to context. Now, when it comes to this, there are some important things that you need to understand. One of which is that there's different time elements. So you need to understand what the simulation time frame will be. If you look at this graph on the bottom left, you'll find that the time units end at 1.3. Then you look at the graph next to that and the time units end at 15. If you have to interpret the results for the first graph, you would definitely assume that these two variables are converging, right? However, when you put it into context in terms of a longer time frame, you'll find that this is actually a magnified picture of the first couple of time units on the second or this middle graph. And if you had to interpret the results based on this pattern of behavior, you would realize that after converging, it actually then oscillates and diverges, which is very different to what you would have thought was happening if you had the time frame incorrect. The other thing to remember is that when you choose your time frame, so if something starts from 2015, how many years of data would you have to use as historical data in your model? I mean, for example, let's say you're looking at population growth. Because there's data available for the last 50 to 100 years, do you need to go back that far? Or can you just use data in the last 5 years, 10 years, and then use that pattern to be able to fit, say, a logistic curve and try and work out what you think the projected pattern of behavior would be for that particular system? So that's the importance of all of that. Andries will take us through the DT, the time intervals as far as time is concerned. But it's also important that we understand then what our historical trends of variables here are. In this case, I've just indicated some pure system response behaviors like just linear or exponential increasing, decreasing. There could be oscillatory motion, patterns of behavior, or a combination of any of these system responses. In terms of the third step, which is our collaborative brainstorming, ideation, and boundary setting, we then include causal loop diagrams in the step as well as system architecture map. Now, we have an entire chapter on causal loop diagrams as well as system archetypes in our book, but suffice to say, our causal loop diagrams illustrate the cause and effect relationships between our variables. I've got a very, very light image here, but this is generally what your causal loop diagram would look like with its reinforcing loops and balancing loops. So essentially, we want to understand what the cause-effect relationships are between these variables. However, when we draw something like a system architecture map, we're not looking for cause and effect relationships or these directional quantities that are linked to the variables. We're trying to understand what the upstream and downstream key variables will be that are impacting our system problem, as well as any pertinent externalities that are specific to that environment. Now, in our engagements, what we found is that not all of these tools actually work to help the customer understand the problems. Some people love the causal loop diagrams, and some people would love the system architecture map. So you have to sort of accommodate all of these stakeholders that are involved in the project. And so the more tools you have for system understanding, the better. And it really does make a difference to represent the system in various ways, not just through causal loop diagrams. Our fourth step is then system analysis. So as far as system analysis is concerned, in our experience, what we found that there's a lot of institutional misconceptions that your system dynamics modeling software is the start and end of the system dynamics modeling process. So a lot of people just, okay, give me the software, let me jump into this thing, and off they go. Absolutely not the approach that will allow you to understand what's actually going on in order to model the system problem. So as far as the system analysis is concerned, what we also found in this step is that sometimes we end up with data that have gaps in it, especially projects that involve energy data or any other data where we have gaps. We then require things like exponential smoothing or numerical interpolation or classical regression or any of the data analysis techniques that will help us to try and get our data in a form that would be easier to input into the model. And of course, the analysis could be any method, but it is an important step before you get to model development. In our experience, what we found is that this step has resulted in several offshoot projects and ended up with smaller models, not system dynamics models, but Excel-based models or Power BI platforms to help people actually understand the data better. And people want to use these models in that form even before we get to the system dynamics model structure. So this step for us is actually critical, and it's really where the majority of your time should be spent. The next step that we go to is the model development and design. Yeah, I've just got a structure that would allow us to incorporate an S-curved equation. And the software that we use is supplied by IC Systems. Since 2010, we've been using Stella. I know that Andries actually uses iThink, and he might even have a very, very old version of Dynamo on his computer, if anyone is familiar with that. But for us, the software works in terms of being able to also develop engagement platforms. And we've been using it for a decade. My God, that's long. We've been in this quite long. In terms of the model development, you should actually understand which modules and submodules you need to develop, or have a good understanding of that based on the preliminary work that you did in terms of establishing the causal loop diagram as well as the system architecture map. For this particular step, you would then specify what the decision rules are, do your parameterization, initialization, and establish what your mathematical relationships will be between your variables. So what's also important here is that every rate of flow in the stock and flow structure constitutes a decision point. Hence, it is essential to specify the decision rules relevant to each of these decision points. We'll actually have a little bit of a demo in terms of understanding our calibration and validation step with Andries in a few minutes. This is just one of the engagement platforms that we've developed for a current project that I'm working on that's got to do with recycling renewable materials, in this case, your turbine blades, so that we can work on a circular economy. And so by adjusting a lot of the levers and trying to change initial conditions, we can then have an idea in terms of the relative difference in terms of, as far as your results are concerned for the different recycling options. And obviously there's lots of projects that we've developed, but this is just an example of how it helps us to try and interrogate the system further. Yeah, again, I won't go into detail in terms of the model testing and validation, because Andries will take us through a show and tell that will explain this in more detail. The second step, which is your model handover, this in a real environment is very, very important. So you don't just want to build your model and have it shelved. You want to make sure that people will use the model. And one of the ways to do that is to ensure that people have training in terms of being able to use the model. A lot of times we arrange a lot of training sessions on a completed model, and we leave the model owner alone. They then run the model independently, and then we go back to them after a certain period of time and go through the issues that they experience. Because what we found is if you run the model, it looks easy enough, people are happy. But when they start running the model, that's when they actually, the real understanding comes in. And then they realize the gaps or what they need to actually ask in terms of trying to better understand the model. So you go back and you make sure that process is completed. If there's any minor changes to the model, then you as a system dynamicist can then implement those changes and customers happy, hopefully. In terms of the last step, what we also found in our environment is something that also helps to ensure the long-term sustainability of the model, is that you should revisit the model at certain intervals, depending on what the model is and the purpose of the model. In some instances, data is updated every 6 months, in some instances every year. But whatever the time interval is, you need to establish a schedule where you go back and you update the model in terms of the data, you make minor changes to accommodate any configuration changes in the system. And this also means that the model is always current and never outdated. So that's it from my side. I hope that was interesting. I'm going to hand over now to Andries.
Thank you, Nalini. You probably noticed my camera's got some issues, so that's why I look like the Rainbow Nation. So what we'll do is basically I'm going to use the concept of population model, which is a very simple model. It basically starts off with a birth rate. You need some births, which increase your population, and your population is then controlled by the deaths. And I like life expectancy, where I know some people use a death rate, which I don't agree with. But basically, the question that arises to me is that the only fun models are the ones where the results are counterintuitive. If I expect a certain outcome and something different happens, it intrigues me, because the question then becomes is, do we know if this model is correct, or is this result just bad coding? And does this model really accurately reflect what's going to happen in the future? And this is where validation and calibration for me is critical. Nalini, if you can go to the next slide, please. So basically for me, validation is the process that confirms the model elements behave in the way that we expect them to behave. So as I said there, the insightful models are the ones where the results are counterintuitive. And then usually the difficult bit is, how do I explain them? Now, if your model is validated, it means all the components work correctly. If all the components work correctly, then the answer should be correct. And then if we look at the calibration process, it says basically it's the process that confirms that the model can replicate the historical data. So if our assumptions and our structure is valid, then the calibration process should give us a reasonable confidence interval about the history, which means that this becomes a useful model. And then suddenly we can start explaining the counterintuitive results that we get because of complex interactions. And Nalini, can I share screen now? Let me take over. Okay. Okay, so basically the screen I've got in front of you is a process that I would go through to validate whether the elements in my simulation is correct. So what I've done here is very simply, I've created the model that says there's an initial population. This population increases if there's births, and then there's a birth rate. Now, if I use an equation that basically says birth rates times the population, I would expect that I would see exponential growth. So let's check that and confirm. If I'm going to say there's no growth, I expect my model to stabilize. The population should be stable. So let's see what happens if I increase this to a 1% growth. And now I start seeing something that looks linear, but maybe it's not really linear, because let's try 1.5. And now you start seeing how that exponential growth starts appearing. And we can keep going until we get to a number that's probably, I mean, this used to be realistic in the 2000s in South Africa, where we had a population growth rate of 2.1%, which meant in the long term that the population was going to grow exponentially. And we've proven this, so this concept works. If we go to the death side, so basically I'm starting again with my population of 40 million people, and I can now type in a life expectancy. The equation here is very simple. It says the population divided by the life expectancy will give me an F distribution, which basically says on average people will die given the life expectancy. Some will die younger, some will die older. So let's start off with a 2000 life expectancy in South Africa, which was a scary 42 years. And then we can step it up to, let's say, a 60, which I would expect fewer people to die. So my exponential decay is slowing down. And if I go to 80, I should see it go even lower. I mean, slower. So there now, so basically I'm happy that my population, my birth system works, my death system works. So now let's go to the population system. And I've basically got here my birth rate. 2.5 is a bit rough. I'll do 2.1. Oops, 2.1. And a life expectancy of 72, which seems reasonable. And there I can see what's happening to my population. So in general, the system seems to be working. If I try and put in a 42 year, I expect that that curve, oops, now we start seeing, okay, if the life expectancy is way too short, even with that birth rate, we have a negative growth. But, you know, it's still, this model so far has been quite well established. Let me just check this one. This is the one. I'm just going to try something here. So let's try and see what happens if we switch on the Sensi specs. Actually, I think that's what calibration does. Okay, that's what calibration does. What I've done here is I've set up a sensitivity table. For those of you who have never done this, got more complicated in the later versions of, I think, Nalini is quite correct. Actually not correct. I don't have Dynamo on any of my systems, but I do have a working copy of, I think, version 2.01. And I have a working copy of the first Windows version of, I think I got the first one in the world at the time. So what I've done here is I've basically set up a calibration process that will allow me to take, actually, sorry, this was the wrong one. Let's just go one back. Just want to go one back. Okay, sorry. Just here to population. So I'm going to just run that sensitivity run here for you at population. So basically what I've done here is to say, if I take a series of birth rates and I take a series of life expectancies, I can create a method to very rapidly run through multiple scenarios. Now, the trick here is I usually dump this straight into a spreadsheet, into a table, export it into a spreadsheet, and then I can do all sorts of magic there to check and confirm that the model is behaving correctly. And of course, if you want to know exactly what your setup was for that sensitivity, you can extract it here from the graph, or if there's a table, you can just extract it from by clicking on the question mark. If we go to calibration, what I've done here is to say, hang on, the real life in a place like South Africa is that in reality, so I just want to switch this off quickly. In reality, we have a birth rate. I don't know if you can just see if I can move. In reality, we've got a birth rate that over time has moved from 2.1 and it's on a steady decline. So what we are seeing is that over time, the birth rate is reducing. But what we're also seeing is that over time, our life expectancy is increasing. Various reasons. It could be because of better healthcare. It could be because of better nutrition, etc. But now what we can do is to start run a simulation that now gives me a possible future, and I can calibrate. So I can basically, into this graph, I can map out what happened in the last year, and the last 20 years, and then basically project what is going to happen in the next 10 years. You'll see my model runs from 2000 to 2030. If I go to even more calibration, I've done a little cheat here, which we show you what happens when I run this baby. I'm just going to switch that sensitivity run on to allow me to, it won't affect these parameters here. So I just need to check something. Okay, this is fine. So what you'll see now is I've created a whole range of results. And now I didn't change the life expectancy or the birth rate. I basically kept the same profile as I had in the previous simulation. So what did I change? I used one of the other built-in functionalities, which is called the normal functionality, which basically says we've got a situation where we're basically sitting here with an average, and we can assume that there's a normal distribution on the birth rate and the life expectancy, and then that there's some sort of a variance, standard deviation on that. So if I change that and I say instead of 0.5, I make that my data is really unreliable, which is in many cases true, then let's see what happens if my standard deviation instead of 5% is 20%. And now suddenly you can see that the range is increasing. Now, the reason why I use this for calibration is I can now map, I can take this, I can put it into a spreadsheet, I can calculate the average, I can calculate the standard deviation, and I can then compare that to the reality and see if I've got a decent confidence interval to make sure that the results make sense. So that's the basics that I want to finish on calibration. So let me just go back to I'm going to just stop this screen. I just want to share another screen. Okay, so this model is slightly different because one of the things I found is I'm a self-taught modeler. So I basically got a copy of, I think, I installed it, and I started making mistakes. And I battled and I battled, and eventually I started learning how to test whether I'm making sense. So what I've done here is I've basically created a tiny little model that allows me to test functions. So for example, one of the things I find intriguing is if I've got a river system and I have an accident and there's some pollution that gets dumped into the river system, how can I trace how that is going to be running through the system? And the simplest way would be for me to say, okay, let's simulate what happens when we introduce, after a period of time, we introduce a perturbation in the system. So the model I use here basically has a function I want to test. It has a flow. It's got a conveyor. The reason for the conveyor I'll demonstrate just now. And then it's got a stock that's only got an inflow. The nice thing about stocks that only have an inflow is that gives you accumulation. So if you want to see if a result is exponential, that's the place that you'll see it. If you want to see if it's decaying, that's again the place that you'll see it. So the 5 graphs I've got here is I've started with the function I test, so I can go back to see if I'm seeing what I'm supposed to see. I look at flow 1. Then I look at what is happening, what I call instantaneous. That conveyor of mine, I've given a time interval of one time element, which will basically then tell me how it's going through the system. Flow 2 is just to confirm that what's going in is the same that's going out. And then the cumulative graph at the bottom right basically will tell me what's happening in my cumulative stock. So what I'm going to do is I'm going to demonstrate that pollution system of mine and say if time is equals to 5, then I want to enter a something that impacts the system, and I'm going to just give it a value of 5, and I'm going to say only that instant I want something to go into the system. So let's see what happens. Okay, so flow 1 has a 5, the function I test gives me the 5 as I expect. The flow in gives me a 5 as I expect. Instantaneous tells me that something's wrong because the value here over a full-time unit is not the 5 that I anticipated. Flow out is 5, but here you can see again on the cumulative, I'm not getting the 5 that I expect. So what have I done wrong here? So let's try another thing, and let's say, well, maybe the problem is that I go back to 0. So let's see what happens if I make that one 5 as well. So this will just run through 5s. So I get a straight line, that's 5s, and that goes up to 5. And cumulatively, oh no, that's not exactly what I'm looking for. So let's go back to this function and we try and do something else. So let's try a pulse function. And let's do 5,5. And let's run that pulse function. Okay. So now something, oops, sorry, I've got a space in there. That's why it's not like it. Sorry. Let me just rerun that. Oh, it's still behaving badly. So what am I seeing here is, oh no, actually it's correct. So what am I seeing here is when I put in the pulse function, the value that the pulse function gives is after 5 periods, it goes to a value of not 5, but 5 divided by dt. And my dt at the moment is 0.25. So it basically gives me a 20. So I'm seeing exactly that the system now does the calculation I would expect in flow 1. And it now gives me an instantaneous, it gives me a 20. However, if I look at the end result, oh, I still get the wrong number. So let me just reset all of this and try again. I'm going to try and just get it clean, and let me try something else. I'm going to put in after 5 periods, I'm going to put in a pulse of 5, and then I'm going to delay for another 5. And let's see what happens now. Now we see an interesting behavior. We see the pulse function causes the input value to go to 20, which is correct. It's 5 multiplied by 4. And it does it every 5 units. We see the same thing replicating here. Instantaneous goes up to the value of 5, which is what we expect. Our cumulative counter goes up to 5, and then it adds the additional 1. So let's try and make sure that we only put in 1 pulse. So what I'm going to do now is do another little cheat here to say if time is equals to 5, then pulse, and this is the last form of the pulse function. I just say pulse 5, else 0. And if we run this one, we'll see the red line does exactly what we expect. So I can now replicate that pollution load specifically. Of course, there's many ways to skin a cat. So you can also do exactly the same by a little cheat here to just say 5 over dt. And we get the purple line to do the right thing. And then, of course, there's the real cheat, which just says time and we make this a graphical function, and we basically, oops, say 5, and we say 5, make that 5. We make this a discrete function, and booms, we get very interesting. So what you see now is that that pulse that I put in only goes up to 5 and then drops. But what you'll see is instead of being a narrow pulse, it's actually a flat curve. And cumulatively, this gives us exactly what we expect to go into the system if we try and do that. And you can see here it slowly builds up, but the green line also ran on top of my purple and red lines. So basically, by using this little tool, I've now managed to test the different functions, and it becomes quite easy to play around with complicated functions. I don't know if there's anybody who wants to try and test an alternative through this little tool. If we want to put that through the questions, I think I've used up all our time. So maybe if we go back to the moderator for this now. So guys, I'm done. If you're ready to take over there, unless there's many questions, which I can't see.
We do have a couple questions, Andres, and I'm just gonna bring this up. Just give me 1 second. I'll just get it, and then we can start answering them. I'm not sure if we have time to go through all of them, but let's get started. And this one, share. Can you guys see me screen in the questions? Can I think I'm not exactly sure if there's any. These questions are specifically for Nalini or Andres. I think Nalini, do you want to take maybe 1 or 2 of these questions to start? And then we see, Andres, you can also help Nalini to answer these ones. We also, I think we have some questions in the chat, but we can start from this one.
The top 2, sorry, Roel, maybe the top 2 questions are the ones that get me all excited.
Do you want to get to this one then? How to deal with
let's start with that one.
Changing.
Yeah, the thing that got me really hooked onto system dynamics was that I tried to run optimization models for complex systems, and very soon came to the realization that 10 minutes after you've optimized the system, somebody goes and changes one of the parameters, and then you've got to rerun it. And the reality is that life is a dynamic system. So decisions are getting made continuously. Depending on the quality of decision making, people are either making long-term or short-term decisions. And that is why when you start off, the structure is so important, because the structure guides what those decisions are. And then the system will basically run that. And that's where I showed you that average function or normal function that I used. You've also got a random function that can generate random numbers. And one of the useful tools is basically to then say, okay, I don't know exactly how the system is going to pan out over a period of time, but I can put enough elements in my system that says that the average has got standard deviation, and it will vary throughout the time period in which I'm simulating. And then run the simulation for a statistically significant number of times. In theory, that's 30. I normally do 50 because that's just good maths, some extras. And then basically use that result. What can you say? I mean, you basically then get a result where you can calculate an average and the standard deviation for each time unit. And use that to do any hypothesis testing in terms of calibrating that back to what happened historically. For example, try something interesting like predicting the interest rates and the impact it has on housing development in a developing country. Now, that is something where econometric person will give you a perfect fit to history, but a complete uncertainty regarding the future. In system dynamics, I can't get a perfect fit on history, but I can get a 95% confidence interval that my average is close enough. And then I can predict or project into the future and say, if the conditions remain the same and the decision making remains the same, then I will end up with a reasonable answer. So the thing about it is that the system changes continually because people are making decisions or elements are changing. The structure itself unlikely to change. I mean, it's, take an air conditioning system. It's a good example of this, where it is a control system that very simply looks at a sensor to say this is the temperature, it compares it to a set point, and then it basically tries to heat or cool air and circulate that air and try to change the measurement at the sensor. The reality is then in between, there's a huge office space, there's desks, there's chairs, there's people moving, everything that affects that system. So, it's not impossible. I think it's critical to understand the structure and underlies that and what is driving that decision making that gets you there. I don't know if that answers. Sorry, I can go on for hours. This is, to me, this is fun.
Thank you, Andreas. Let's get to other ones. Maybe Nalini want to answer a couple of this.
Sorry, next one, mine. Data is irrelevant.
This one?
Data, yes, that one. Data is a second order problem. The reality is that we've got an underlying structure that is causing certain behavior, which causes or is a result of certain decision making. So if you understand the problem and the structure properly, then data, you need very little input. And I think that's the power of system dynamics. You really need very little input data to replicate what is happening. And whether it's a small community, I mean, sometimes you get some really complicated problems, like how do you simulate a lottery as a business proposition? I did one a few years ago, 98% accuracy. I tracked it for about 5 years, and the simulation itself was 98% accurate with zero data because we never had a lottery in South Africa. So, but by understanding the structure and studying how people behave and looking at how other countries manage their lotteries, I was able to generate a very simple model, get extremely powerful and accurate because it used that understanding of how people behave. So I think one shouldn't stress about data when you start looking at a problem. You should understand what's the underlying structure that's causing decisions. How do people make the decisions? And then, let the model do the outcomes. That's what the model is for. If the answer is obvious, then there's no point. If there's million of data points and it's going to give you one answer, then there's no point. But if there is, like you have here, there's few data points, and you really have to understand the system, then it gets really interesting to start building a simulation for that. And yes, resource economics, which I believe is this problem here, is something that's also quite interesting to try and simulate. Now give Nalini the easy questions.
Oh, yeah, okay. Okay. I saw a question on how many variables. Okay, how do we know that the model needs no more variables? Is it always good to have as many variables as possible? Is it up to the modeler to choose the variables that matter the most? Now, this is a very interesting and pertinent question to the modeling process. Now, I wanted to picture a graph where the x-axis is complexity, and your y-axis is your level of understanding. And you can imagine a bell curve. So what this actually means is that as the model becomes more complex, your level of understanding increases, but you reach a peak in terms of the maximum level that you could understand at a specific complexity level. And as you proceed and the model becomes even more complex with even more variables, you find that your level of understanding actually decreases because now the model is too complicated. So you need to actually hit that sweet spot that says you have to try and get that right level in terms of understanding versus complexity. To know how many variables you actually need, this is the importance of steps 1 to 4 before you get to model development. You have all of the preliminary steps that you take, which includes a lot of stakeholder engagements, a lot of work group members that have the tacit knowledge besides using your data. When the discussions happen and you formulate your system architecture map, you understand the causalities on a subjective level largely, but you understand this via causal loop diagram iterations, you will get an idea of the key variables that you need. Now, the variables that are chosen are also a function of the purpose and the focusing question that you need to answer in addressing the system problem. So there's always cases where you engage with people and they love the model so much that they're like, but why don't you include this and more stuff? And so you have scope creep quite easily. But that's why you need to actually establish your system boundary, and that's why you actually need to have these discussions up front. And that's where in John Sterman's book, he presented the model boundary chart, which also helps because then you can engage with people and establish your endogenous variables, your exogenous ones. The ones that are important, they should be there, but they're excluded because of the scope of the project. So it's things like that which are preliminary before you get to the model, which will help you actually understand the sort of variables you need to include in your model. I hope that answers some of that.
This one is done.
If there's no documented, where is that?
We answered that one, Nalini. I think this one's maybe this one that has quite a lot of votes. The first one. What are the main challenges to model public policies in developing countries where quantitative data is scarce and some qualitative data is available? I think it's very similar question that Andreas answered, but if you maybe want to elaborate a little bit too, your thoughts.
For us, what we actually do is when we're dealing with data that's not empirical data and relevant to our country, we look at a country who is similar in terms of economic development and has a similar economic structure to South Africa. And we actually use that as a proxy for our behavior in terms of what the system could potentially exhibit. So that's one way in which we deal with it. Yeah, I think that's it on my side. That's what we've done for a lot of economic and energy data. You know, let me give you an example as well. Let's look at electric vehicle market penetration. Now in South Africa, we don't have established targets. We have one because of the green transport strategy that says we have to have 3 million cars by 2050 because of our commitment to the Paris Agreement. However, we don't exactly know how many cars we will have in 2030 or 2040. So what we would do then is we would say there is documentation and reports available in terms of the global targets and forecasts in terms of electric vehicles by year 2030 or 2040. If we understand electric vehicles is still seen as a luxury good or luxury item, which means that we could then use GDP as a proxy to represent the situation. By that, what I mean is, if we say South Africa's GDP is 0.0057 of the world's GDP, we can then take that value and multiply it by the global number of electric vehicles that are targeted by a specific year. We should get a fairly good idea in terms of what we should be looking at. So it's approaches like that, which then help us to actually get more quantitative data and analyses.
If I can maybe also come in here, is I think part of the dilemma with a simulation tool is that you need to implement some rule set, you know. So once you understand what the structure is like, you have to then implement the rule set. Now I've used an air conditioning system as an example. The rule set is relatively simple and it's consistent. The behavior of the air, etc., might be complex and complicated and affected by many other things, but the rule set itself remains consistent. The dilemma you've got in many of the developing countries, including our country, is that the decision-making rule set's not consistent. So what might work today might not work tomorrow. So in that case, I think, and again, that's where system dynamics does give you opportunities, is where you can then look at a scenario type approach, where you create plausible scenarios, and in terms of how that decision making could behave, and then basically you can implement the alternatives and say, look, the structure is not going to change, but the way that people make decisions within that could change. And therefore we can see 2, 3, 4, whatever the number of different potential outcomes. And you can start doing sensitivity analysis around that. But I don't think there's an easy solution to guarantee that you'll get good results. You know, yes, you know, two countries might look the same. The politicians might not behave the same.
Nalini, if you allow me to just add to what you're saying, I think actually people would be surprised with the amount of data that the developing countries have nowadays. And as Andreas said, you don't really need a huge amount of data to build a great system dynamics model. And you'll be surprised if you look at this data, and we have great resources nowadays to get quite good data to build system dynamics models. I think we have more 5 minutes. If you want to take 1 or 2 more questions, Nalini, Andreas.
How can you professionalize system dynamics without a formal education, without having a master's? By professionalize, you mean becoming sort of an expert in system dynamics? I assume that's what's meant there. The way in which, well, Andries did say he sort of got by in a very different individualized approach. However, in my case, I did not study system dynamics on a tertiary level. I used it after learning how to develop system dynamics models on like by myself. It was a lot of bedtime reading and a lot of experimental work. And because of my interest in the subject, I just carried on getting hold of resources and just trying to develop models after we established a very specific software that the company could use, which in our case was IC Stella. And so as you develop more, as you engage with customers in the environment, we took the standard conventional system dynamics approach and adapted that so that it worked for us. And so too, as we got more experience, we actually optimized our process, and with an optimal process, we then increased our knowledge base. And so it was a bit of a feedback loop there. So I don't believe you need to actually get a formal education for you to actually understand system dynamics and get familiar with the modeling methodology. However, it does help to have a mentor or a coach that has the relevant experience. Else you could end up with a problem, like simple problems, which is like integration errors and not understand whether the structure is causing problems or whether it's an accumulation of errors because of the integration method you're using, for example. So you do need to have some sort of mentorship and guidance from somebody who is familiar with the methodology, but it doesn't necessarily have to be through a formal system, in my opinion.
Nalin, if you allow me, sorry, Andres, I was just going to suggest that we actually have quite a couple people, good professors in the field that could share their experience and complement this question. I think Len is here. Len, I mean, I'm getting you off guard, but if you could maybe share your thoughts on this and also talk about the summer school. And we also have in the audience, Karin Chichakli. He has a great experience on Practo's approach. If I'm just gonna find you guys and unmute. Len, asked to mute. And Karin, I think I saw you here. I'm sorry if this is making you guys uncomfortable, getting you guys off guard, but I'd love to hear that. Len, are you unmuted? Can you talk? Maybe he's not.
So maybe while we're waiting for them to activate, my approach to system dynamics modeling and I mean the whole computer thing is that it's a tool. So I basically cut my teeth on trying to solve problems. I had complex problems to deal with. And I come from an engineering background, and building a simulation just makes sense sometimes. And so the approach I've always followed is that if I understand the problem fundamentally, if it's a simple problem, the answer is obvious, and then there's no point in building the simulation. If the answer is not obvious, then it is worthwhile to explore whether it can be simulated. And once the simulation runs in your head, it's worthwhile to go and bother to build the simulation. But, you know, it's like violence, building the simulation is the last resort. Once you've reached the point where you're 100% sure that you can't just solve it by looking at the problem, then it's worth bothering to build the simulation.
Fernando, I'm here.
Hi, Karin. Can you maybe share your thoughts on this question as well? I would love to hear.
Yeah, that was Len, but this is Kareem. Yeah, so first of all, I agree with Andres that SD is a tool, and a formal education can be useful in a lot of circumstances. But if you want to apply system dynamics, you just need to do some training. And as Nalini already said, having a mentor is really critical to move forward and become very good at it. This society has a very good mentorship program that you can sign up with and get help from experts. So I would recommend you do that. If you have a deep interest in system dynamics, see, system dynamics should always be paired with something else. You don't want to use it by itself unless you're trying to be a generalist. If you have a deep interest in system dynamics and want to know a real lot about it, then perhaps you would pursue a master's or a PhD.
Thanks, Karin. Len, could you maybe share a little bit of the summer school and if this is a good approach to start, maybe formal education?
Fernando, can you hear me?
Yeah, we can hear you.
Sure, I've been looking at the questions. I also put a lot of links in the chat for general information. And when I see questions like this, it reminds me of Jay Forrester at a banquet at the System Dynamics Conference. oh gosh, he might have been 96 years old at that time. And someone asked him what his profession was. And he responded, I am a student of system dynamics. And of course, the entire audience started to laugh because he's the fellow who invented it. So the point here is that learning does take some time. There are many, many free resources. That's the way I started. But then I went and took formal education after that. It's not trivial. The summer school, I'm an instructor, I have to admit, I think is a very quick introduction, but maybe Kareem mentioned this, you will not be an expert after 4 days in summer school. There are user groups for all the major software tools. I sent a bunch of links on learning, both from the society and from the Creative Learning Exchange. It's definitely a journey. It's almost a way of life. What Andres said about how do you know? I have some criteria myself. One of them is the problem dynamic? Does it take place after time? Or is it optimization? Is there feedback? Does doing one thing today cause something to happen later, which then will cause my initial decision to be challenged? Are there delays in the system? So an action today might not see a response or a corresponding event for days, weeks, months, even years. And then finally, the criteria I use is there uncertainty? All models are wrong. Some models are useful. We want to develop useful models about very complex problems, and I think system dynamics is a great approach to that. I use it every day on all kinds of problems, but please make use of the tools, the websites, the user groups that are out there, and obviously the society is the place for your one-stop shopping about what is system dynamics, how can I learn it, how can I make contact with other people in my area through the special interest groups, for example, or the national chapters, which, by the way, let's give a plug for the South Africa chapter. They're doing some great work there. And then I'll be quiet.
And maybe just where you should start. Kareem, you spoke. So if you go back to Stella 2.01, there was a little manual called Business Process Improvement that was written by two ladies in the administration. They weren't system dynamicists or developers in the organization, but they basically went through the process of how do you use this tool to improve the business. And I read that on a plane, and by the time I landed, I had my proposal ready to get my boss to give me the budget to buy the software, to buy me an Apple Mac, because in South Africa, we very scarce on Apple Macs. And in 1992, I was off and running and making some serious mistakes, but hell, I had a lot of fun to try and get this under the what was the title of the booklet? That was called Business Process Improvement. It's a very scarce and rare Stella manual. I've not seen it subsequently, and I know there's other people are also looking for it. I have a copy somewhere hidden in my files.
Thank you, Andres. Nalini, I think we have just a few questions about the book itself, and I think that will be good for you to maybe promote a little bit of the book and talk how people can buy it. I think I saw in here somewhere. Yeah, so this is the question about the book. You're muted. Sorry, Nalini.
Sorry. Okay, can I just share my presentation again? I've got one slide
sure.
which talks about the book. share this and scroll down to the book. Oops. This is the information on the book. To buy a copy of the book, you can actually drop me an email. This is my email address. We are, like I explained to Rebecca, in the process of trying to figure out how to facilitate international sales a little easier. We've already, I mean, since the book's launched like a month and a bit ago, we've actually sold close to 35 books already. So that's locally, and we haven't had issues, but in terms of courier costs and that sort of thing, we can share more information if you can just email me directly. The third author who isn't present but did contribute to the book as well is Professor Josephine from Stellenbosch University. So the book has been co-authored by Andries and Josephine. Yeah, I actually have the copy. It's like, oh, I don't know if you can see it this way. It's like, we try to make, okay, I think Andries did lose a lot of people because he gets so excited with these system dynamic simulations that he jumps 200 levels higher. And I think he doesn't quite sort of contain his excitement, so he goes into the complex stuff very quickly. However, the book takes you from the basics. I mean, from like one stock and an inflow and an outflow. I promise you, it does start from the basics. Very, very simple. In fact, it takes you even a way before that. It starts from systems thinking. And so it gives you a lot of tools that you can use to try and do root cause analysis, as well as approaches to try and support your systems thinking skills. Because I believe, like all of us, we're all systems thinkers. We just need to sharpen our skills. So we've got lots of exercises in the book, hands-on exercises, examples of sure, there's just quite a lot, and I promise you it does start from very, very simple, taking you through to intermediate levels of modeling. But for us, system understanding is critical, and you find a lot of that then covered in the book. If you do want to try and confuse Andries in return for his presentation, you can email him at this email address. And I'm sure he'll be able to give you more information on that. While I have my slide up, the South African System Dynamics chapter will be hosting their 9th System Dynamics conference this year in November. This year we've made the conference theme a bit flexible to allow more contributions on the applied systems thinking space. So registrations have just opened, and we hope that we'll get a lot of participation internationally and support for our conference. In terms of the chapter, sorry, I'm just like stealing the time I've been given here to talk a little bit about our South African chapter. So our chapter was actually recognized in 2014 by the International System Dynamics Society. Our current 2021 council members is Andries Botha, he's the president. We've got Dani Booyens as vice president, myself. I held the post of president for several years. And then they needed a breath of fresh air, so I moved aside. And then we have somebody who's actually attending with us, right, the session, and that's Corné Deploy. He's our competitions organizer. And I want to say something about our competition. Our competition has been run 3 years in a row. We've made it now international, so we're hoping to get far more participation, not just from Africa, but from the rest of the world. Our key sponsor is IC Systems. So they offer the free software for the duration of the competition, so that people can use the software to develop the model relevant to the competition theme. So for that, I mean, we've had lots of support from Karim and his team. We will be running yet another competition. So we're going to launch free workshops, and Corne will be sending out a lot of information in terms of when the registration's open. It's a free competition, by the way. Prizes are cool. It's like really something that you have nothing to lose by entering. So all the novice, and it's not just for the seasoned practitioners, the guys that are also starting out, please give this a shot. And that's it from my side.
Thank you so much, Nalini. I think we're just on time to finish it. I would just like to thank you guys. Thank you, Nalini, and thank you, Andreas, for this great presentation. For me personally, it was great. It made me remember when I started studying system dynamics, my first classes in the University of Bergen. And I also like to thank Majid Brahimi. He's been very helpful, great volunteer for the society. And if you want to volunteer to the society, you can reach out to me, and we can definitely get some projects for you. And just one last thing, we're sending out a survey for you to give us feedback. Please do so using the link on the email you're probably getting just now in your mailbox. And that's it from my side. Rebecca, do you want to wrap up with something to say?
Thank you. I would just like to thank Fernando and Mahid for really pulling together a nice set of events. And I put the link on the chat for you. There's quite a lineup of seminars as well as events from other chapters that we're trying to consolidate there. If you have things to add to the list, let us know. And we look forward to seeing you at our next event.
Yes, thank you so much. See you next time, guys.